Hello, it's Yasmin again from ThatITShow. And let's start learning about how to program in ARM. What we have in front of us is an ARM simulation or development kit. Such kits are usually used when you need to develop something. And the idea is that it's much simpler to do development on a piece of hardware that is going to emulate everything that you can possibly use in your particular case. So this kit, for example, has switches, toggles, buttons, numbers, different headers to whatever, USB, VGA, audio input, audio output, network, and so on. So this is a physical motherboard that contains a chip that is able to be an ARM processor, and it can simulate how an ARM processor works. But more importantly, it enables you to run the ARM architecture assembly and also to debug it. So you can use such a board to be able to connect different devices and to do step-by-step analysis on how your application works, what is your application doing right now, and different things that are possible in real life scenario. So this thing would be something that you would use to develop your software between the part when you actually write the algorithms and everything else in the assembly, and the part where you use that assembly compiled into something that can be executed on ARM chip, and then using this in the actual device. So this device is just a step between your you writing something on your computer and then running it on some hardware, and then actually using actual hardware. So for example, I don't know, a mobile phone or any other device that contains the ARM processor. So why is this important? Because this is hardware. This has some value. It needs to be purchased, and this is one of the best boards when it comes to starting to learn ARM. And Altera is also specifically known for a good FPGA board. So this price that is shown here is the price that you can expect for this kind of a board. But the reason why I'm showing you this board is because I want to introduce another simulator. Now, if you go to simulator.01xz.net, you're going to be greeted with this one. This is the computer system simulator that was written with an idea of trying to emulate exactly the board that I was showing you in different architecture modes, so that you can actually see how this is going to be behaving when you have a board in front of you. So you can imagine this as being a board or a simulator of a board that enables you to completely do your debugging and simulating in software. And then when you're actually ready to switch over to the board and try to communicate with actual devices, you can do that. Why is this important? Because if you choose a good simulator, and this one is one of the best, you're going to end up with a system that is going to enable you to have minimal initial investments. So you don't need a board, you don't need anything other than your computer. Specifically, you don't need even to install anything. This is running in the browser. And you can try out and learn how the assembly language works. And then when you have a particular reason to switch over to hardware and attach sensors, attach external devices and so on, you can do that. And you can do that easily because you have already done all the development, since this is trying to mimic the board as close as possible. So on the left side, if you just log into simulator 01xz, you're going to see that on the left side you can choose the architecture. The ARM v7 that we are going to be using is not the only one. You can also use NIOS2, you can use different MIPS architectures, and RISC-V. I'm not currently interested in trying to explain all of these. you can take a look at the documentation. The documentation is extensive and it is going to help you work with the simulator. What I'm interested in is to just go quickly through how this simulator works and what can you expect of it. So what I'm going to do, I'm going to choose the first one. So I'm going to use the ARMv7, and I'm going to be using ARMv7 DE1 SoC. So system on a chip, DE1. This is the simulator of the board that I showed you. Press go. And you are going to be greeted by a pretty crowded screen with different things. Now, let's quickly go through what we are seeing here. I'm going to start in the middle because this is probably the easiest point where to start. This is the editor. This is where you write your assembly language, and you are going to write a code here. Once you're finished with your code, you can use the buttons up here to step over, step into, continue, and so on. Also, you can use this button to compile the code and load it into the processor. And you can choose, if you want to, you can choose and switch from ARMv7 assembly to C. We are interested in assembly, so we are not going to be using C. And this is just a placeholder that represents the global start label, or the label that denotes that this is the start point for your assembly language. Once you compile your assembly and it is loaded in the memory, you're going to be seeing your memory disassembled here. So you can see, since we have only what we did in the assembly was we only mentioned two labels. So there is a .global start and then the start. It just says here, this is the start, and this is start of the memory. So address 0. And nothing got compiled. So we are just switched to the memory view, or this assembly view. And this assembly view enables you to see what the particular value is in the memory in a particular place. And you can actually see this value being disassembled. The memory view shows you the memory as hexadecimal values. So if you need to take a look at the memory and take a look at in different blocks of the memory for some reason or the other, you can use this memory view. What you're usually going to be doing, you're going to be switching from editor to disassembly, because the editor enables you to edit, and the disassembly enables you to see how your instructions ended up in the memory and what the instructions actually are. Also note that since ARM has a set instruction length, so it's 1, 2, 3, 4 bytes long, you are going to be seeing this formatted as a column that has different things. This is the BGE is just the imprint representation of the value that is stored here. So we are going to be seeing, once we do some code, we're going to be seeing different instructions here. Just right now, this is just a placeholder basically. Continuing with this interface, on the left, you see that we have some registers here. These registers are divided into the 3 different groups. You see D registers, you see S registers, and you see R registers. You can take a look at the documentation to see what those are, but the ones that we are going to be mostly interested in are general purpose registers called R, since we are going to be using them to store the data that we are working with and controlling. Also, you see here that we can see the flags, because there is a stack pointer register and flag register that enables you to see what the status of the flags is right now. And there are some different registers that I'm going to be mentioning later, because we are going to be doing branching and so on. So I'm going to be mentioning different registers that are important when we come to them. Next comes the call stack. Call stack is a tab here, and this call stack enables you to see which instructions were called and where were they called from. I will be mentioning this much more when I create a loop or I create a procedure to show you how this thing works. Trace enables you to see what were the instructions that your program executed. So let's say this is the timeline of what was executed when your program was running. Then you can set breakpoints. So you can give it breakpoints here, and you can create a point that says, okay, at this particular address I need to be watching for a condition, so I can actually create some sort of a condition in a particular address in order to stop the program once the program reaches this waypoint. You can also watch different parts of the memory, because sometimes you want to see how many reads happen in a particular size of the memory, what was written there, and so on. You can take a look at the symbols or where the actual parts of your application are. This is less important to us because we are not going to be going too deeply into the assembly language, so the symbols themselves are not useful. And also you can see the counters on how many instructions you executed, what was the runtime, how quickly is your simulator behaving in simulated millions of instructions per second, and so on. So this is this one. Here in this smaller part of the window, and you can resize all of these, you can see number display options. Number display options is a way of telling the application how do you want to see the numbers and how do you want to interpret the way that everything is shown. If you take a look here, you can see that I switched from word to, for example, byte, and I can see individual bytes here. And then if I switch to word or half word, I'm going to be seeing 2 bytes being a half word, then 2 bytes, then 2 bytes, and so on. Then if I switch to word, I'm going to be seeing 4 bytes. So this is just the way that memory is being displayed. Also, I can switch from hexadecimal, which is normal, to signed decimal, for example. So I can actually see what the value is in decimal signed numbers. So not binary, but decimal signed numbers. I can also switch to how many numbers am I seeing, or how many locations in the memory am I seeing in a particular row. I'm going to be leaving this at defaults. Hexadecimal is much more useful to me than using decimal numbers, so I'm going to be switching those also. And this is the display thing. The editor thing enables you to do code completion. So if the editor sees something that it is able to complete, for example, a loop or an instruction or something, it can help you and complete the code. This is something that we have already seen in different editors, so this is just a nice thing to have. It's not something that is obvious, and usually when you become more fluent in assembly, you're going to be stopping using this, just simply because the instructions and everything else are going to just be natural to you, so the code completion is a nice thing to have, but usually you're just going to be ignoring it. Then showing the source, meaning the parts of the source that are going to be showed. I'm going to be showing you how this thing works. It basically works in this mode. And if I say none, some, or all, this is going to change depending on the code that we are going to be showing you. But the thing is that since I don't have any code, nothing is changing right now. Now, also, there is a possibility for the simulator to check automatically for some normal errors. For example, the program counter has to be a multiple of 4, simply because every instruction, when in this ARM, is 4 bytes long. So if we are pointing to an instruction and need to move to another instruction, we are going to be moving by 4 places, so 4 bytes. If the program counter is not a multiple of 4, this means that something has happened that misaligned the program counter, and this is not going to end well, because this means that basically you're reading the wrong bytes in wrong order, and you are going to have problems later. you can take a look at what debugging checks are enabled. In the start, everything is enabled. So you are going to be having a lot of help from here. For example, I don't know, stack pointer moving outside the stack frame and so on. If you remove the debugging checks, you can also work. This is going to be completely fine, but it is possible that you're going to be running into some kind of a problem that is caused by a simple error that could be just catched or noticed by the system by using these debug functions. The last things here are which system we are using, so we can switch to any system as we did in the first screen, and also how much memory are we going to use for the simulator, and you can go as high as 2 gigabytes of RAM, but since we are dealing with a small processor and simple tasks in the assembly language, this is going to be a complete overkill as it is here. Down here there are messages. Messages enable you to see all the different things that have happened and all the different things that your simulator has done. So you can see that right now, for example, we did decompile. So when it pushed when I was in the editor, when I said compile and load, we did decompile, and it is notifying me which command has it actually used and what it did with different files. The idea of this simulator is that it is using in the background, it is using a simulator that actually exists, or the compilers and everything else that actually exists on Linux. So this is more or less simulating Linux and then running the compiler on top of it. So it's a strange way to do things, but on the other hand, it's just completely in tune with Linux philosophy of just not reinventing the wheel every time. Now, on the right side is the, let's say, input and output panel, and these are the things that you can see on the board. The board itself has some LEDs or diodes, has some switches, has some push buttons, some 7-segment displays. It also has a JTAG UART. JTAG UART is a serial port that is directly connected to the board that you can use to communicate with the board itself in your application. Since we are running on the Cortex A9, you also have timers. There is a private timer and watchdog timer that you can use for your applications. There are different watchdog timers, interval timers, and so on that you can use here. There is a VGA pixel buffer, or more specifically, this is actually a VGA screen that you can see when you are doing something. So this emulates a video card, so you can see what you are doing when you are debugging something. Car World is something specific for the University of Toronto. They decided that they are going to be having, since every university and everybody who is trying to learn something has their own approach on how to learn assembly. What they did is they created a car simulator that has steering and acceleration as commands, and then it has X, Y, Z and speed and sensors as the result. This is the controller that they are using connected to the board that I mentioned. So this is an actual piece of hardware that they're using. As everything here is, but it is being emulated in order to make it easier for us to work. Also, down here, you can see that we have two parallel ports. And these parallel ports are emulated as bits. So this is 32 bits of information. We have an audio card that is, you can switch it to, you can see the base address, what the base address is. It's an 8 kilohertz audio card. There is a keyboard and mouse emulator. There is a video in control emulator, and there is ADC and generic interrupt controller. We are going to be using just a small subset of these things, since we're going to be interested in just simply starting and understanding the concepts. And so we are not interested in, for example, audio, but you can use this. Now, the thing that we need to understand when it comes to this interface is that you can, by using these drop-down menus here, for example, you can switch from 8 to 32 LEDs. This is because the data size, or the size of the part of the memory or location of the memory that we are pointing to and we are mapping to these LEDs is 32 bits. So there are 32 LEDs actually. The switches can also be switched to 32-bit mode because there is 32 bits. Push buttons can be 32 buttons. 7-segment displays can have 8 segments because we are dealing with 4 bytes. So 1, 2, 3, 4 bytes, and so on. So you can actually, on the drop-down menu, you can change some things. The reason why it is showing only a couple of LEDs and a couple of switches is because it's much easier for if you are doing something, it's much easier to deal with the first couple of ones. For example, 10 LEDs, and I think this is 10 LEDs and 10 switches. You can also, using the interface, you can check the switches and manipulate them. So, for example, if I want the switch to be switched on, I can just put a check mark here. Or if I want to switch it off, I can clear the check mark, I can clear all and set all. Also the buttons. The buttons are different than the switches in that respect that when you push the button, your button gets depressed, or it gets cleared after a few cycles, and the switches are going to remain set. Now, what are these numbers here? These numbers here represent the memory, or the part of the memory where this particular input-output device is mapped to. So, for example, if I take a look at this part of the memory, I see that my memory screen has changed. And this memory screen here represents the LEDs here. I'm going to just show all of them. And I'm just going to, for example, put one here. As you can see, my LED on the location of binary 1 has switched the state, so now it's on. This is because the actual location FF and then 2 and 5 zeros is this location is mapped to these LEDs. So if I put a value here, for example, FF and then 000000, I'm going to be setting the first byte, or the most significant byte, so the first 8 bits, and the rest of it, all the remaining 3 bytes, is going to be zeros. So by directly manipulating memory, I can set the LEDs. When it comes to switches, they are mapped to the location that ends with 40. So if I put the switches and set it to some position, once I do a refresh here, I'm going to be seeing that this location has changed. And the reason why this has changed is because I made the change here. So for example, let's just set the 1. If I do a refresh here, you can see that this location contains the value of 1. So this represents something. Also, I can change the values depending on which location I'm working with. One thing to note, LEDs are a display thing. So if I change the value here, I'm going to influence the LEDs. But I cannot change the value in the memory by pushing on the LEDs, because the LEDs themselves are unable to change the memory. They're just reading the memory. The exact opposite happens to switches. So I cannot change the status of the switches by changing something at this location. I cannot just say FF and then push enter, because I cannot using memory, I cannot change the physical status of the switches. But if I change the switches themselves and do a refresh, I'm going to see the value change here. Now, push buttons are, as I said, almost exactly the same, but they are located here, so this location here. And if I do a refresh, I'm going to see some value here, output here. If I clear the push buttons. I'm going to refresh and see a 0 here. So this is the location for the push buttons. The push buttons have an additional thing here. There is a memory value, and then is an RQ value. The RQ value represents or notifies me that if a button is being pushed, this interrupt is going to be generated. So I can see which interrupt is being generated for each different device. And as you can see here, the devices that are used directly to either present information to the user, so LEDs, and get the input from the user, so switches, don't have the interrupts. But something can be changing during the runtime, and that can be offloaded by using the interrupts, has the interrupt. So 7-second display is not going to have the interrupt because it's just displaying something. But for example, JTAG, since it's a bidirectional protocol and it enables you to both read and write from the device, it has an interrupt. Also the timers, also everything else here, parallel ports and so on. So this is how the emulator looks like. And this is the emulator that I'm going to be looking at and using when I'm going to be dealing with different examples. And to finish this thing, I'm going to be opening sample programs here, because you can actually use this assembly or simulator to both open, save, and share the different examples. And also you have sample programs inside the simulator itself, just to see how it works. So for example, if I do an infinitive loop, and if I just put it here, you can see that this is probably the most simple application or assembly code that you can create. It says start, and then it just branches to start. So this is just a basic loop that just jumps to itself. Now, I'm going to show you how this thing works by first compiling it. It is going to switch here, and what is going to happen is that this value here, so we can see the assembly language here that we have compiled, and then we can see how this looks like. So B0, this means just jump to this location. We don't care about anything else other than this, because this is just going to be running in a circle and just jumping to this location. To verify this, we can say continue. This is going to become green and change to running. And we can go to trace and see that we are jumping from the start to the start. And you can see that nothing is happening. We are just jumping. So if I press stop, you can see that we jumped a lot to the location of the start. If I go to the counters, I can see that we have executed this many instructions. So an amazing number of instructions. We were running for 16 seconds, 6.7 seconds, and this is 26.57 million instructions per second. So we have done what, 300, if I'm correct, 305 million instructions during this period. So this simulator is running at a pretty decent speed, and this is the reason why people like ARM processors. Even when they're doing something, I would say, completely useless, they're quick. Now, let's just show you another test, VGA, because this one is much more complicated, and show you there is an example here. You can take a look at it by yourself. I'm not going to explain it right now. And if I do compile, it's going to switch to this assembly. It is going to show me what was assembled and where, which instructions was which, with all the comments. I can now go back and just show you how the source code says sum. So this is going to change into when there is a reason to show the source code, it is going to be shown. For example, here, because it wants to explain that this is going to jump to the label right char, and the label right char is somewhere. Let's find it. So here. Or I can just say to show the entire source code. So then we're going to be seeing instruction by instruction what was executed here. The reason why it is sometimes using some, sometimes using all, is because it doesn't make any sense to just duplicate the entire thing. So move R1, comma R9 is the same instruction. So it doesn't make sense to show it here, but you can use it and you can show it if you want. Now let's run this thing. I have a disassembly run. I want to switch to, since this is dealing with VGA, this is the VGA card, and I'm going to press continue. And I'm going to be seeing this VGA output extremely quickly changing colors. As I said, the amount of instructions that this thing can do in a second is astonishing. So this is going to be too quick to be normally shown, or to be normally shaded or animated. So we are going to be just seeing a blur of colors. We can also work with this one and just then deal with trying to slow it down and so on. But I'm currently not interested in this, simply because I want to show you how this simulator works, not how the application works. And this is the end of the introduction video. In the next part, I'm going to be dealing with programming. Okay, now let's start with the first example. The first example is going to be a pretty easy one. What I'm going to do is I'm going to be creating just a simple addition. Simple addition is the same thing that I used when I was showing you how the how 602 works, and I'm just be pasting part of the code because I don't want to need to retype it. Now let's deal with first and try to explain how the code works and what does this code do. Now the instructions themselves are going to be just two. I'm going to be dealing with the instruction called move and the instruction called add. Move is simple. It takes a couple of arguments, and the instructions in this assembly are read from right to left. So what does the first move mean is move the value of 13. So I'm using the hashtag as a value, and then I'm moving this to R2. This register here. Then I'm moving the value of 14 to register 3, this register here, and then I'm adding R3 plus R2, and then I'm going to put the value into the register R0. So as I said, reading from right to left, so this means R2 plus R3 is going to be put into the R0. So the R0 is going to contain the result. Note a few things. First, I'm not using the memory. This is strictly using the registers. The reason why this is possible is because the ARM processors have a large number of registers, and the reason why they do this is because they are trying to avoid talking to the memory as much as possible. Talking to the memory is slow. If you are able to work with the registers, if you are able to deal with your registers in such a way that you don't need the memory itself, you are going to be much quicker while running your application than what you would do if you are using the memory. Okay, now let's try and compile this. Compile succeeded, so it is happy with this. And then let's step into the application. Stepping into meaning let's start the debugger and just go step by step. You can see here that helpfully the debugger or this assembly has translated the values that I gave it as decimal values into hexadecimal values. So it says that this number is actually 0xd, so meaning d meaning 13. And when I execute this, or I executed this instruction, the R2 became D. My program counter jumped because it jumped to the next location that is going to be executed. If I do a step into, my value of E is going to be set to R3 and my program counter jumped. Then if I step into, I'm going to be adding those two numbers and the value of 1B is going to be written to the location R0. That's it. Now if I do a step into, my application is going to be just jumping, and this is going to be something that is going to make no sense at all. Now, the reason why this doesn't make any sense at all is because I didn't create a way for the application to stop. My application was just created in such a way that I basically gave up. I didn't tell to the processor anything to do after my application was finished. What I can do, I can leave it like this, or I can just, if I want to make it look prettier, let's say, by prettier I mean basically make more sense, I can go into the editor and I can create a loop. So for example, I can say, let's deal with this one. So this is going to be stop, and I'm going to be doing a branch underscore stop. So now if I do compile and load, and then if I go and do a step into, I'm going to be moving, adding, and then just going and stepping here. This is okay, because if I press continue, it is going to end up in the infinite loop. Everything has been done in the processing, and I can just stop whenever I want to, and it is not creating exceptions. When I see these messages down here, this is because my code didn't stop and it was just executing completely random bytes through the memory. So the reason why I used the stop was that I wanted to create, I would say, a controlled way of stopping my application, so that my application hasn't actually stopped, but my application itself was behaving in a predictable way, so it is just looping onto itself in a particular location. Okay, in my previous example, what I did was I did some adding, and then I said, okay, I need to create a way for my application to stop. What I did is I created the infinitive loop. This is obviously not okay, but let's try to explain why this is not okay and what should be done and what can be done. Now, let's first define the environment. The thing that we are dealing with here is that we have switched over from the environment we have before. So the environment we had before was basically 6402 itself. When you are running the assembly on older processors, you're expecting that your application or your assembly language code is going to be running on the processor, and the processor is yours by definition. So you can do everything on the processor, and the processor, you can directly influence everything. When we are dealing with newer processors in the ways that newer languages are working or the newer applications are working, usually your application is going to be running in something called user mode or normal mode or whatever, and there is going to be a supervisor, or there is going to be an operating system that is going to be enabling you to run. So when I execute this thing, it is usually going to be executed under an operating system. So I'm not going to be running directly on the processor. I'm going to be running directly, but there is going to be someone supervising me, so giving me the allocation of the memory, enabling me to use the processes, enabling me to use CPU, and so on and so on and so on. Now, this way of ending the application is not good. Because what I did here is I didn't end the application. I'm just running in circles. So I need to stop my application forcefully. I'm going to be needing to end task, as it says in Windows, or just killing it in Linux. So obviously this is not okay. I'm going to delete it. And what I'm going to do is I'm going to be trying to create the real way to end my application. Now, how do I do this? There is a way of talking to the operating system. So the operating system is in charge of everything that you may need as an application. Let's position you now and let's imagine that you are the application. You want some memory allocated. You want to stop. You want to access some other outside devices. You want to deal with an interrupt. You can do something. So what can happen, and what is interesting is that you can interact with the operating system by using something called supervisor calls. Supervisor calls are the way in which the operating system that is running on the processor is linked to a particular location in the memory. And when you are running the supervisor call, it is going to be basically your application is going to be raising the interrupt, and then your interrupt is going to be interpreted by the operating system above, and then it's going to do something. So the most useful and the simplest thing that we can do is we can ask the operating systems to shut down this application. So I can tell to the operating system, can you please exit my application? So can my application just be stopped? The way to do it is I'm going to be doing these two things. So I'm going to be moving value of 1 to the register 7, and then I'm going to be calling an instruction called SVC, supervisor call. And SVC just says to the SVC0, says to the operating system, please do something for me. Now, if I compile and load this, and let me see what was the problem. There is no problems here. Okay. So if I run and load it, if I step into it, I'm going to be moving. Okay. I'm going to be adding. I'm going to be moving value of 1 to R7. And then I'm going to be using the supervisor call. When I go here, it is just going to basically stop. If I stop and restart it or reload it, and then continue, I'm going to see that my simulator requested breakpoint, so it stopped. Now, what does this mean? This means that I requested from the operating system that I want my application to stop or to exit, and the operating system fulfilled that instruction. And now I have to understand how. Now, the most important thing is this R7 register. R7 is the register that is used to pass the instruction that I want to talk to, or that I want to use. This instruction is called the syscall or system call, and you can find links to all the different system calls in the Linux documentation, specifically in the headers for the Linux kernel. And you can see that for different architectures, you're going to be seeing a lot of different calls. So, for example, this is for Linux 4.14.0. It's inside the Linux, in the syslinux header, so you can take a look at the files and then see what the headers are for different architectures and so on and so on. But I'm not interested right now in this. I'm interested in just the simple solution or the simple table. And this table is going to be pretty similar across different architectures. Since almost every architecture needs some specific commands to be able to use the system. Stuff like reading something, writing something, exiting, opening a file, closing a file, creating a file, and so on, are something that is normal for almost every architecture there is. This is the thing that is interesting, because my assembly language application does not exist in a vacuum. I cannot just say, okay, I have written, I don't know, an application that is counting to 10. And then what? I need to either an exit, I need to return the control of the application back to the operating system. Maybe I want to do something other than counting, so I need more memory. Maybe I want to write the results to the file, so I need to talk to the file. And it would be much, much, much too complicated to open a file, write something to it, then close the file directly from the assembly language. Since I don't know where the disk is, and I don't know how the disk looks like. I don't know what the file system looks like, and I have absolutely no idea how this is structured. So I would need to create the entirety of the whatever is needed to both talk to the disk, talk to the file system, enable the file system to be read, then understand how the structure looks like, and so on and so on and so on. So what I would usually do, and what I would probably do, I would talk to the operating system, because the operating system knows how everything looks like. Talking to the operating system is done through this. So for example, if I need to read a file, I am going to put the number 3 into the register 7. Then I'm going to be putting the file descriptor, or the location that was given to me when I opened the file. I'm going to put this file descriptor to the R0. I'm going to be putting the buffer, or the information that needs to be, where the information is going to be read from the file to the R1. And then I'm going to be telling, using R2, I'm going to be telling the operating systems how many bytes do I need to read from the file. So this is my way of talking to the operating system and telling it, okay, I need to read from the file. You can also write to a file, you can open the file and close the file, you can create a file, you can link, and so on and so on and so on. There is an enormous amount of things that you can do through the system calls. Since you are using the system the way it is intended to be used, it's the tool that you are using in order to give you resources, allocate your resources, and the tool that you can use to simplify programming. Because you don't want to be responsible for everything. You don't want to be talking to the operating system in such a way that you are responsible for the CPU and all the other processes that may or may not be running on your computer. You also don't want to know which disks does it have, graphic cards, I don't know, different devices that are connected to it. You just simply want to, for example, read a file or write a file or do something. So this is done through the system calls. And the way that this thing works is that in this particular case, I just called the system call 1 and told it, okay, that's it. I want to exit. What I can also do, I can put the error code in the R0, and this is the way that I'm going to be notifying my operating system what happened. So I can have a return code for the operating system that is going to say, okay, nothing happened, so my application finished correctly, or something was happening, so I had a problem with the operating system or my application, so the operating system can know what has happened. Now, the reason why we're doing all this is because we are running under the ARM. You will note that if you take a look at any documentation, you're also going to be seeing different other Linux system call tables for different other architectures. For example, x86 has its own call table, and its own call table doesn't have the exit instruction in the same location, but on the other hand, the names of the registers are not the same. So RAX, so register AX, there is an AX register, there's a register called G1, G2, G3, G4, and so on. So different registers are designed or implemented in this architecture. And you can see that x86 has something like 332 different system calls. Then there is ARM 32-bit. There is, after quite a few system calls, much more than what x86 has. There is ARM 64-bit. It is also using different registers to pass the arguments to the system supervisor or the supervisor call. Then you have another architecture here called x86. So this is the 32-bit version of the location of the architecture. This one has the exit, for example, in the first, but we are using AX register to pass the information. So you can see that the system calls are changing depending on the architecture that I'm using. Since I'm using ARM here, I'm going to be using the R7 and putting 1 into it because the table tells me to do this.